Okay, so on Monday, we were going over position versus time graphs. What we can read, interpret, okay, calculate, etc. from a position versus time graph. And yesterday we did our lab, okay, and yep, the Chromebooks didn't work super good yesterday. Sorry about that. That activity will, of course, involve using y equals mx plus b for position versus time graphs, so calculating velocity, position, time, okay, all of those things that we've been going over. So just as a quick review, okay, if we are looking at this graph, which we analyzed on Monday, okay, if we've got a graph that looks like part A here, okay, what is that object doing?
Going forward at a constant velocity.
Going forward at a constant velocity, okay? We know it's a constant velocity because it goes the same distance every second, okay? It's not accelerating, okay? It's traveling at a constant velocity. If the line is flat, what is the object doing?
Stopped or not moving.
Stopped or not moving, okay? In part C, still traveling at a constant velocity because it's a straight line, it's just diagonal, but this time it's pointed down, which means the object is moving at a constant velocity backwards. Okay? Its position is becoming more and more negative. All right? And we also said that between E and F, both of which are showing an object moving forwards at a constant velocity, okay, which one was faster? E, because it's, let's say faster. Steeper, yeah. Okay, it's steeper. And we know that the slope of a line on this type of graph is equal to the velocity of the object. So the steeper the line, the faster the object is going. Okay, so that's the stuff we learned about interpreting a position versus time graph. Now, if I wanted to calculate a few things, there are a number of things I can calculate from this graph. Okay, one of them is the total displacement. Okay, between any 2 points on the graph. And I calculate total displacement by taking the final position and subtracting the initial position. All right, so if, for example, I wanted to calculate the total displacement between 0 and 6 seconds, okay, my final position would be positive 6 meters. My initial position would be 0. So if I go final position minus initial position, I find that my displacement between 0 and 6 seconds happens to be, oh, not meters per second, 6 meters. And I would also have to say forward or positive or something like that to indicate the vector, because displacement's a vector quantity. Everybody follow me there? Okay, we did a few like that. I can also calculate the total distance. Okay, if I'm calculating the total distance, that means I need to add all the sections together. So essentially I'm doing final position minus initial position, but I'm doing it for every part of the graph and then adding all the sections together, right? So if I wanted to calculate the total displacement to, or sorry, the total distance traveled to 10 seconds, okay, I know that it goes 6 meters here. It goes no meters there, and then it goes from 6 to negative 10, which is 16 meters. I almost wrote 26. 22 meters, okay, for that one. That would be my total distance traveled between those 2 points. Everybody follow me there? Okay. If I wanted to calculate velocity between 2 points, then I just use this formula. Velocity equals displacement divided by time. Okay, and I take my final position minus my initial position divided by the time elapsed between them. Okay, and then for speed, I take my distance and divide it by my time. Like we said, this could be a visual representation of one of the word problems we did at the beginning of the year. Right, so we would use the same formulas and basically the same technique, okay, to answer these kinds of questions. That ringing a bell for Monday? So what we're going to go over today is velocity versus time graphs. Okay? Then we're going to work on some graphing problems that you might get on, let's say, a quiz or a test or something like that, okay? Just to get some experience with those. And then next week we'll probably move into acceleration. Okay, so before we get to velocity versus time graphs, this position versus time graph, okay, is showing an object doing what? Okay. Yeah, okay. In fact, it's accelerating in a couple of different ways. 4 different ways, actually. Okay. In which part of the graph is it increasing its speed in a forward direction?
From the y-intercept.
Yeah. Well, I'm not quite all the way to B, but close. Yeah. I would say like section A, so from the y-intercept here at 0, okay, to probably about here. Okay. That part, yes, that would be an object that is increasing its velocity in a forward direction. How do we know that? Well, every time interval, the distance it goes increases. Right? The length of this vertical line gets greater every time I go across. Okay? The only way that that can be happening is if it's going faster and faster. Everybody okay with that? All right. Now, something that you won't have to do, but will need to understand how it works, is sometimes a question might ask, what's the instantaneous velocity at a certain point? Okay? Now, instantaneous velocity is different than average velocity. Up until now, we've been dealing with average velocity. How fast is the object going between these 2 points? Instantaneous velocity says, how fast is it going right there, at that instant in time, rather than over this interval? Does everyone follow the difference? Okay, so most of the time, if you've just got a line, a graph that looks like that, the instantaneous velocity at any point on that line is equal to the average velocity because the object's not doing what? That it's doing here. It's not accelerating, so its instantaneous velocity is its average velocity because it didn't change. Okay, but along here, if I calculate the average velocity, okay, it's going to be some imaginary straight line, but that's not going to be the instantaneous value at any second along the way. Okay, so if it asked me, what's the velocity at, let's say, point A right here, how am I supposed to get that? Like, it's at one point in time. How far do you travel in an instant? No matter how fast you're going, really. None. An instant means basically no time elapses, which means you don't possibly have any change of position during an instant. So there has to be another way to do this. So what we have to do is we have to understand that on a position versus time graph, the slope of a line drawn on that graph is equal to the velocity. Remember that from the other day? Okay. Now, I'm going to explain to you the only thing that I understood in university calculus. Okay? It was the first day. I understood nothing after that. Okay? I passed the class by memorizing the examples in the textbook and writing them down on the final exam and getting part marks for method, which was smarter than half of the people in my class. I'm not saying that that was a triumph or anything, but it got me through calculus. If you've ever looked up here and thought Coderre's good at math, you're quite wrong, actually. Okay? So here's what a curve looks like to a mathematician. A curve is an infinitely large number of infinitely small straight lines that are strung together. Okay? So when a mathematician looks at this curve, they see what you would see if you looked at a low-resolution picture or watched a low-resolution video. What do you see when you watch something or look at something that's low resolution?
It's pixelated.
Yeah, it's pixelated because a computer can't draw curves. It can just put squares together, zeros and ones. Okay? So as long as you are watching something in high definition, the pixels are so small that you can't see them. And so it looks like a nice smooth curve. But if it's in low resolution, the pixels are large enough that you can make them out and things look jagged and pixelated. So when a mathematician looks at this curve, they see all the little tiny straight lines. does each one of those straight lines have a slope? It does. Every single straight line has a slope, and every little one of them changes just a little bit, and on this line gets steeper. So, if I want to calculate the instantaneous velocity right here at point A, I need to find the slope of the tiny little line that exists right there. How am I going to do that if it's this big? It doesn't have a y-intercept, it doesn't have like y, change in y or change in x, okay? How am I supposed to get its slope? The answer is I cheat, okay? This is what I do instead. I just make that line longer. So I use my ruler. I know it's smartboard, it's cheating, but I do this. I draw what's called a tangent. Okay? A tangent is a line that touches a curve but doesn't cross it. That means it's parallel to the curve at that particular point. That means it has the same slope as the little tiny line that exists at that point on the curve. Everyone following me there? Is that line now long enough to get a change in position and a change in time? And I could get the velocity. Okay? So, as we can see, if I move along this line, along this curve, right, the slope of the line that's there, oops, that's not the line I want. Okay, like if I move further down on this curve, okay, the slope of the line gets ever shallower. Okay, if I go up that curve, that line gets steeper and steeper. Okay, indicating that yes, it is in fact going faster and faster. Now, what's going on after this point right here to this point right here? It's no longer speeding up. What's it doing now? It's slowing down. It is. Okay? Because if I look at the slope of this line, it starts to curve the other way. That means instead of getting steeper, it's getting shallower. Right? In fact, right here at point B, how fast is the object going? Okay. Remember how we said if we drew a line that was tangent to the curve, its slope would be the velocity? That line's tangent to the curve. What's its slope? Okay. So at point B, the object is instantaneously, at least, stopped. Okay. Now, after point B, that line starts to get steeper again. So what is it doing?
Decelerating?
Oh, it already decelerated. This just deceleration means it slows down.
Oh, it moves backwards.
Yeah, not just moves backwards, but actually accelerates backwards. Okay, now I'm going to tell you here right now, guys, that in physics we don't use the term decelerate. Okay, because the term decelerate implies that we come to a stop. There are lots of times where I can slow down but not stop. Okay, so we use the term accelerate for any change in velocity, positive or negative. Okay, so a negative acceleration means to possibly go slower, but also possibly accelerate backwards. Because in order to go slower, I actually accelerate backwards. Okay? So imagine it like this. If I put a bungee cord across the classroom and ran at it, okay? When I get to it, okay, I start slowing down, right? Because the bungee cord is pushing me which way? That means I'm actually accelerating that way. If I kept running into the bungee cord, eventually I would come to a stop. And then what? Yeah, exactly. I'd get shot backwards, right? But my acceleration would be the same the whole time. It would be that way. I'd slow down, and then shoot back the other direction. Okay? Is that kind of what this is showing? This is showing something slowing down, and then actually accelerating in the other direction. Okay? And then for this part here, the line's getting flatter again. So in this part, the object is slowing down, yes? Okay, what is this a graph of? Okay, the first part is me accelerating the marker upwards. Once it leaves my hand, it starts to slow down because of gravity. Slows down, for an instant it stops, and then starts to move back down. The rate of acceleration, once it's out of my hand, is the same. It's 9.81 meters per second squared due to gravity. Okay, and then that last part, when I catch it and bring it to a stop, because eventually that line gets flat again. All right with that? I would never ask you that on a test. I'd never say, here's a graph, tell me what's happening. Could we throw a marker up in there? That's totally not fair. Okay? Could I ask you interpret this graph? Yes. Then you could say an object is accelerating positively, going faster in a positive direction, then it's slowing down, coming to a stop instantaneously, then it's accelerating the other way, and then it's coming to a stop again. That I could ask you. Okay? But to tell me exactly what happened, that wouldn't be fair. Okay? All right. Questions there? Okay. That's it for position versus time graphs. So now, we're going to look at velocity versus time graphs, which, as their name would imply, show us what two things?
Velocity and time.
Velocity and time, yeah. Okay, okay, so this graph on the left is a position versus time graph. What is it showing me? What is this object doing?
Moving forward at a constant velocity.
Moving forward at a constant velocity. Okay, we have a slanted line upwards. Okay, it's straight. That means it's not changing its speed. It's changing its position by exactly the same amount every second. That's an object traveling forwards at a constant velocity. Okay, what's the velocity versus time graph showing me?
Moving forward at a constant velocity.
Moving forward at a constant velocity. These two graphs are showing exactly the same object. Okay, do they look quite a bit different? It's because they're looking at the same object from different points of view. One is looking at its position, the other is looking at its velocity. From a velocity perspective, nothing is changing. The velocity is constant. Okay? From a position perspective, the velocity is constant, but the position is changing at a steady rate. Okay? So it's showing us exactly the same object. And we can prove it mathematically. Could I calculate the velocity of this object? Absolutely, right? I can go, all right, I got a nice linear line here, so I'm going to go m equals y minus b over x. This point is right on the line, and its value is 1400. The y-intercept is 100, and the time is 5 seconds. I believe that's 260 meters per second, and that would be okay, is that what the velocity versus time graph is showing me? Okay, this is 200, that's 250, that's 260. That's showing me exactly the same thing. Okay. What's the displacement of this object from the position versus time graph? Oh no, that's just showing you where it ends. So that, you're right, that's totally misleading. No, the graph ends here.
1400.
We start at 100, so 1400 minus, right, it's 1300 meters, right? Okay, so our total displacement according to this graph is 1300 meters. Okay, all I did was go final position minus initial position, exactly what I did up here. Okay, and that gave me 1300 meters. Okay. Could I calculate the displacement on this graph? I have velocity and time. What do I do? Yeah, I use V equals D over T. Okay, average velocity is total displacement divided by total time. I have the average velocity, 260 meters per second, and I have the time, 5 seconds. Should I get 1300? I better. It's a graph of the same thing, okay? Now, effectively, all I did there was take the base of this and multiply it by the height. Agreed? Right? The base was time, 5 seconds. The height was velocity, 260. Okay? And it got me to displacement. Okay. Questions so far? All right. What's that object doing?
Accelerating.
It's accelerating positively. Okay, because its velocity is going from positive 100 meters per second to positive 400 meters per second over 5 seconds. That's really fast. Okay, because that's going from 100 meters per second to faster than the speed of sound in 5 seconds. Okay, so that's really, really, really fast. Okay, so that object is accelerating. An acceleration is the rate at which you change your velocity. Could I calculate the acceleration, the rate at which my velocity changes? That's a weird question, right? Okay, on this graph, I calculated velocity by finding the change in position and dividing it by the change in time, because velocity is the rate at which I change my position. Acceleration is the rate at which I change my velocity. So I calculated velocity, which is the rate of change of position, by getting the slope. Could I calculate the acceleration, which is the rate of change of velocity, by getting the slope? Yes. Okay. Slope always tells you this: the rate at which y changes over x. It doesn't matter what's on the graph. Slope always represents the rate of change of y over x. Okay? So on a position versus time graph, it's velocity, because it's the rate at which you change your position over time. For a velocity versus time graph, the slope is acceleration, because it's the rate at which you change your velocity. Okay? If it was the growth of a plant, okay, so we measured like meters over weeks, okay, it would be the rate at which the plant grows in meters per week. It's always the rate of change of y over x. Okay, everyone okay with that? All right, so what we're going to be looking at coming up here, okay, is that acceleration is vf minus vi over t. Does that look a lot like this? Because it is. Acceleration is the slope of that graph. Because on this graph, y would be my final velocity, b would be my initial velocity, and x would be time. Okay. All right. Could I calculate the displacement of this line here, the diagonal line? I mean, the velocity is not constant anymore, but can that stop me, or am I still good to calculate the displacement? Do I divide it? Right, base times height, but I divide it by something. 2, because now it's a triangle. Okay, so when we were looking at this rectangle, we said that the displacement was the area under the line, because that was average velocity, average velocity times time. Well, is there an average velocity for this line? Certainly there is. it would be halfway between its initial velocity and its final velocity. Agreed? Half the time it would be going faster than its average, and half the time it would be going slower. Well, velocity is the height. If I divide the velocity by 2, does that give me, the change in velocity by 2, does that give me the average? So, am I doing anything different? I'm not. I'm still calculating the average velocity and multiplying it by time. Okay? I'm just going base times height over 2. That's still time times average velocity. I just have to go about calculating the average velocity differently. Okay? So if you want to calculate displacement on that graph, it's the area under the line. Okay? All right. What is this runner doing in, let's say, this part of the graph?
They're accelerating.
They're accelerating. Okay? Because it clearly shows on that graph that their velocity is increasing. Okay? It goes from about 0 to about 8. Then what do they do? What are they doing here? Oh, sorry. Yeah, they're traveling at a constant speed. And then what are they doing after that? Right, they're, well, accelerating negatively. We say, we're still in the habit of saying decelerate, but yeah, they come to a stop. They slow down and they come to a stop. How do I know they actually come to a stop in this case? Is that? Right? The graph ends at a velocity of 0. That means they actually do stop. This is exactly what any like sprinting race graph would look like. Okay? The gun goes off, you jump out of the starting blocks, and off you go, and you accelerate. Okay? And then there comes a point where no matter how hard you push, you can't run any faster. You hit your top speed. And you run at that top speed until you get to the finish line, and then you slow and stop. Okay? That's what any race graph would look like. Is this person particularly fast? Eight meters per second is not particularly fast. Okay? Usain Bolt can run 17 meters per second at top speed. He is a freak of nature. Okay? If you've ever watched any of his races, I know he's getting kind of, in the past here now, but he is a terrible accelerator. But his top speed is so much faster than everyone else's that every race you watch him in looks the same. He starts off at the back, everybody's out in front, and then about 2/3 to 3/4 of the way through the race, he just passes everybody. Okay? Because they hit their top speed long ago and it just ain't as fast as his. Okay? And he just reels everybody in, okay? Eventually, and then passes them, and then by the time he gets to the finish line, he can stop, turn around, and wave to them all, okay, as they come across, because he's just that fast. Everybody with me there? It's fun. Okay, if you ever get a chance to watch one of his races, you can see everybody in the race, they're feeling really good, and then you start to see them tighten up, and they're doing this. Because they just know he's coming. Okay? Okay, does that graph make sense? Okay? Would I ask you to interpret a graph like that? Absolutely. All right, so on this velocity versus time graph, what does that object do?
They have a constant velocity.
Staying at a constant velocity of 5 meters per second. Okay. What's the acceleration of this object?
0.
0. How do I know that?
Because the line's flat.
Line's flat, and the definition of acceleration is the rate of change of velocity. Does your velocity change here? Then you're not accelerating. Okay, calculate the total displacement of this object over the 10 seconds. You should be done now. How far? 50 meters. Yeah. Okay. How did we do that? Average velocity times time. What's the average velocity? 5. What's the time? 10. 5 times 10 is 50. All right. Is that also the area beneath the line? It is. Okay. And I shouldn't say beneath the line. I should say between the line and the x-axis. Because if the line was in the negatives, we'd actually calculate the area above it. Okay. So it's always the area between the x-axis and the line. Okay, so this is a velocity versus time graph as well. They've given us the equation for the line. So the line is y equals 2.96 times x plus negative 0.182. What's the acceleration of this object? 2.96 meters per second squared, actually. We haven't talked about the units, so that was a dirty trick I just played on you. Okay. How did you know that that number represented the acceleration? Right, because it's a slope. Okay, and slope is y minus b over x. I've got ugly. Okay, which for this graph is final velocity minus initial velocity divided by time. Okay, the rate of change of velocity, that's acceleration. Okay. What's the initial velocity of this object?
0.182.
Right. Yeah, negative 0.182. But yes, okay, that is how fast it was going at time 0. So it's actually just slightly below the origin. Okay. Let's say, just for the sake of making things a little simpler, that the y-intercept is actually 0, and that this line starts from 0. Calculate the total displacement of this object. D equals d over t, right? Displacement is average velocity times time. I've just manipulated the formula to solve for d. Okay, so according to this graph, we go from 0 to 30 meters per second. Okay, so our height of our triangle here is 30, or our change in velocity is 30 meters per second. The length of time is 10 seconds. So if I change my velocity from 0 to 30 uniformly, okay, what's my average velocity? It would be 15 meters per second. Half the time I would be going slower than 15. Half the time I'd be going faster than 15. My average would be halfway between my initial and final velocities, provided the acceleration is uniform. That means it's a straight line. Okay, in this case, it is. Right? So my average velocity is going to be 15 meters per second. How did I do that? Well, I took the height of my triangle and I divided it by 2. The height of my triangle is 30. Okay, 30 over 2 is 15. And then I multiplied it by the time. So I got an average velocity of 15, a time of 10, okay, my total displacement should be positive 150 meters. Everybody okay with that? Did I just find the area of that triangle? And it worked, right? Because that calculating that area means multiplying average velocity times time. Okay, questions there? Is that something I'm going to ask you to do? Over and over again. Yes. Okay. Is this object accelerating? It is. It's a velocity versus time graph, showing us a line that's going up, okay? Showing us the object is increasing its velocity, okay? Oh, I forgot to talk about the units. Okay, what's its rate of acceleration? Seth, you told me before, what is it now? 3.3 meters per second squared. Okay, the slope of the line, that's this number, okay, this is m. Okay, that is the acceleration of this graph because it's the change in velocity divided by the change in time, y over x. Okay, now, the units. Why do we get meters per second squared? Does it actually mean the number is squared? Because I don't recall squaring anything when I did this calculation. Right? There's no exponents in there, right? So nothing's actually squared.
Is it like to do with the pixels you were talking about?
No, but yeah, I can see because they're squared. Yeah, I can see where that logic comes from. But it actually isn't. It's because of the units. Okay? When I do this operation, what are the units on the y-axis?
Meters per second.
Meters per second. What are the units on the x-axis? Seconds. So when I go y minus b divided by x, I'm going meters per second divided by seconds. Okay, now, if I write seconds as a fraction, it's seconds over 1. Okay with that? Okay, if I want to divide fractions, what do I do? I see a few people doing this. Which one do I do that to? The second one. Okay, I reciprocate the second one and I multiply them together. Okay, so that's going to mean meters per second times 1 over seconds. What's m times 1? What's anything times 1? Itself, right. What's seconds times seconds? Seconds squared. Okay, that's the mathematical reasoning. Here's the logical reasoning. Meters per second is what we're dividing. That's what acceleration is. It's how many meters per second you change your velocity by per second. Meters per second, or meters per second squared, because it's faster to say. Okay? If you wrote meters per second, that would also be correct, but nobody ever writes that. Okay? We just write meters per second squared. And so that's where those units come from. Okay. If I wanted to calculate the displacement of this object, what would I do? And we've done this on a few graphs now. I calculate the area
Between the line and the x-axis.
right, the line and the x-axis. Now, how many shapes is that? Because this one doesn't start at 0. On this one, there are 2 shapes. There's a triangle over a rectangle. Okay? Would I need to calculate the area of both shapes? I would. And here's why. Since this object didn't start at a velocity of 0, if it didn't accelerate, would it have covered the displacement represented by that rectangle first? It wouldn't. Okay, it absolutely would. Okay? It would cover this distance if it didn't accelerate. But it does accelerate. So not only does it cover this distance, it covers this distance, the area of the triangle, while accelerating. So there's this initial part that it would have done if it didn't accelerate, plus the part it does while accelerating. So I have to add those two shapes together. Now, how do I get those two shapes? How do I get their areas? There's a couple of things I need to know. I need to know the height of this rectangle. I need to know the base of both the rectangle and the triangle. Do I know that already? It's what? 10 seconds, okay. Do I also know the height of the rectangle? What is it? What is it? 4.14, right? This is my y-intercept. It's where that rectangle starts. Therefore, it's the height of the rectangle. So I can do the rectangle right now, can't I? I've got the base of the rectangle, I've got the height of the rectangle. I can do the rectangle right now. 4.14 times 10 is 41.4 meters. Okay, do I have to do a little bit more work on the triangle? Okay, I know where the bottom of the triangle starts. Do I know where the top of the triangle ends? Without estimating. I don't. Can I calculate it? If I'm looking for the height of that triangle, what part of this equation am I looking for? If I'm looking for the height of that triangle, which part of the equation am I looking for? I'm looking for y. Okay? I'm looking for what is the value of y when x is 10. Okay? So I'm just going to plug that in, and I'll get the top of my triangle. Then I'll know the height of my triangle, because I'll be able to go this minus that. Okay? So I'm going to go y equals 3.3 times 10 plus 4.14. That should give me 37. Point 44. All right. Yeah. No, 37.14. Okay, so now the height of my triangle is 37.14 meters. The bottom of my triangle starts at 4.14, so the height of my triangle is actually 33. Everybody okay with that? Okay, so now, this is 33, this is 10, so the area of my triangle is going to be base times height over 2. Okay, so 16 and a half times 10, 165. Okay, so what's my total displacement? What do I do with that number and that number? Add them up. Yeah. Okay, so it's going to be 206.4. Something like that. Okay. I shouldn't do math in my head. Sorry, 165. That's 41.4. I should do math in my head.
You put the decimal in spot, it's 4.14.
No, it's 41.4. It's 4.14 times 10.
Sorry.
Yeah, that's okay. That's yeah. All right. Everybody okay with what I did there? Is this like grade 8 geometry? I mean, really, it is, right? I mean, we had to do a y equals mx plus b calculation, but other than that, it's grade 8 geometry. Calculating the area of a triangle and the area of a rectangle and so on. All right, let's take a break until 9:30, and then we'll get at something else. Okay, what's that object doing? Accelerating negatively, okay, absolutely. And we know that because, well, first off, it shows that the velocity is getting smaller, or more negative, okay? And because our slope is also what? negative. Negative 3.02 meters per second squared. Okay, so we've got a negative slope, which means we have a negative acceleration. Okay. According to this graph, is the object traveling forwards or backwards? That's a tricky one. It's traveling forwards. It's accelerating backwards, but it's traveling forwards. How do I know that?
Because you're still in positive.
Yeah. Do I have any negative values on my graph? All the velocities that are plotted on this graph are positive. They're just getting smaller. Okay? So it's possible to accelerate backwards, but move forwards. We do it all the time. Okay? Anytime you press the brakes in your car, you move forward, but you accelerate backward. Thankfully, your brakes make you stop and not actually move backwards. That would be really difficult to control. Okay. All right, is that making sense to everybody? So that would be like an interpretation kind of question that I could give people and say, like, is this object moving forwards or backwards? And a lot of people, if this was a multiple choice question, would pick moving backwards. Okay? Because we see that downward slope. We see a negative value on the equation, and that all screams backwards to us. But we have to be logical about it and look at the graph and say, every point on that graph is still a positive value. That object is still moving forwards until about 9 seconds. Okay. Could I calculate the displacement of this object? Give it a try. What do I not know exactly that I need to calculate displacement? No, that I can get. I know the two y values. The two y values are 27.5 and 0. What do I not know? I don't know the time. How do I get the time? Which axis is time on? X. So can I calculate the value of x at the end of the graph? This is the end of the graph here, right? What's the value of y right here? 0. So can I use this equation to get x if I know that y is 0? Absolutely. That's the first thing I got to do. Okay? Sure, it's all well and good to know, yeah, I got to calculate the area of this triangle, but I don't know what the base of that triangle is. I have to calculate it using this equation, okay? Solving for x, so x will be negative 3.0, whoops, sorry. Okay. X will be 0 minus 27.5. Okay, divided by negative 3.02. Okay. Okay, is that about right according to my graph? We said it was around 9 seconds, ends up being 9.1 seconds. And I got a positive number, is that important? Because if I get negative 9.1, what am I doing? Going back in time. If you ever get a negative value for time, you did something wrong. Or right if you're trying to go back in time. Okay, but usually we're not. Okay, so now I know that x is 9.1 seconds. Can I get my area now? Okay, height of that triangle is 27.5. Okay. Okay, so 125 meters. Okay, are those kind of things I might ask you to do? They are, but don't worry, we're going to spend lots of time on this. Graphing is important. Okay, we're going to spend lots of time on graphs. Okay. All right. In your digital workbook, where you can look on the screen here, okay, in your digital workbook at the bottom of page 3 for Unit 3, okay, are these same questions that I'm going to blow up on the board here. Okay, I would like you guys to try those. The first one that's going to be on there is actually a position time graph, so you've got to shift gears back to position versus time. Okay, and try and answer that, and we'll go through it here in a few minutes. If you get down that one, move on to number 2, okay, and so on here. So. All right, so this one wants to know the total displacement. This graph is showing me position and time. If I want to calculate displacement, that's final position minus initial position. According to the graph, the final position is 0.5 meters, and the initial position is 0.2 meters. Agreed? Okay, so I'm just reading those values off the graph. So that's going to be 0.5 minus 0.2. That's positive 0.3 meters. Right? Now remember, distance, you got to do section by section. Okay. Give you a few minutes on that. Okay, let's look at the other parts of this. Oh, I left that recording. Okay, so if I want to get the total distance traveled, how far do I go in this section of the graph? Does my position change? Then don't go anywhere, do I? Okay, so that part's 0. Then I go from 0.2 to 1. That's 0.8 meters. How far do I go here? 0. Okay, and then I go from 1 back to 0.5. That's 0.5 meters. 0.8 plus 0.5, 1.3 meters. Okay, I'm just going section by section because distance is scalar and doesn't care whether I go forwards or backwards. All right, if I want the average speed, average velocity, have I already done half the work for that? Okay, I already calculated the thing that goes on the top of that equation right here. Right, so average velocity equals total displacement divided by total time. That's 0.3 over, that would be 7 seconds. Okay, so that's going to give us 0.04, positive 0.04 meters per second. And then if I wanted to do the average speed, speed is total distance over total time. Again, I've done more than half the work for that one already. My total distance is 1.3 meters divided by 7 seconds, and that should give me 0.19 meters per second. Okay, are these pretty basic mathematically? Mathematically, they're pretty basic. I still have to be able to get the parts of the graph. I need to know what to get from the graph. Okay, and then I'm just plugging it in to b equals c over t. Okay, why didn't I use y equals mx plus b for anything on this graph? Is it one line? There's no equation for this because it's not one line. You can only use y equals mx plus b if you got one line. Okay, this is a trick with many parts. I can't do it for that. Okay, so if you're meant to use an equation, you'll get the equation. Okay, since this one didn't give you the equation, you weren't meant to use it. Okay, give that one a try. Sorry guys, I'm passing back a lot of quizzes here because that was 40 minutes. Okay, so let's have a look at this one here. The first thing I want to know is the distance traveled. Is distance scalar or vector? It's scalar, so it's not final position minus initial position, okay, because that would imply there's a direction. So in this one, I got to figure out how far do I go in each part of the graph, and then I add them up. Okay, but they only want to know to 90 seconds, which I know this is a terrible picture. That's where 90 seconds is right there. Okay, so that means in the first part I go from 0 to 400, so that would be 400 meters. How far do I go here? 0. Okay, and then I go from 400 back to 200. So my total distance to 90 seconds is 600 meters. No direction because it's scalar. All right. They then want to know the displacement from 20 seconds to 80 seconds. All right, so from 20 seconds, here's where I am at 20 seconds. That means my initial position is 200. Okay, and then to 80 seconds, this is 80 seconds. Right, so my final position is 300. Displacement is final position minus initial position. 300 minus 200 is positive 100 meters. I have to put the positive on there because displacement is a vector quantity. All right with that. Speed over the whole trip. All right. So I've already done a bunch of the work for that. Okay. I went 400 here, and then I went 400 back. What's my total distance? 800. What's my total time? 100. So 800 divided by 100 is 8 meters per second. Okay, that's where we get that one from. And then lastly, my average velocity is 0. Because where do I end up? Same place I started from, a position of 0. Okay, I started at 0 and I ended at 0. Okay, just because I end at 0 doesn't mean my displacement's 0, but because I started there too, it does. Okay, this is making some more sense. We're going to practice this some more tomorrow. We have a short class tomorrow. Remember, altered bell schedule. You guys are done at 11:46 tomorrow. Okay? Next week, we'll be doing a fair amount of stuff on velocity versus time graphs and acceleration. Okay, and then we'll be moving on from there to our next lab. Okay.